Now, what we're going to do today, starting today, is we're going to formally start Unit 2. And this is more like a normal chemistry class, not a math class like Unit 1 was. We're going to be talking about periodic table today, what the symbols mean, what the numbers mean, and you're going to be doing some other work with some chemicals, looking at the electrons, protons, and neutrons. Okay, so let's get over here and okay. This is a periodic table, and it's rather an old one. This is a newer one, actually. And this is the part that's new down here. You notice up there, it's missing. Okay, so it goes to 118. And I want to talk about what all these numbers mean, what the letters mean. And also, we're going to be talking a little about how it's organized as well. Okay. All right. Mendeleev. Now, I'm pronouncing his name incorrectly, right? She's my Russian expert here. So what's the official pronunciation? Say again. Mendeleev. Mendeleev.
The letter.
Okay. Back about 150-ish years ago, maybe about 180 years ago, actually, there were two people that were very organized. One was a chemist, one was a geologist. And they had all the known elements at the time. There weren't a whole lot then. And they wanted to make some organizational kind of a schema for them. And what they did is they put them in order. They put them in order of atomic mass at the time. So there was probably 25-ish elements at the time they knew about. And then, hydrogen, lithium, blah, blah, blah. And what they noticed were, and they wrote down chemical characteristics of each one of those. And they noticed that all of a sudden, the chemical characteristics started to repeat themselves. So every time it repeated, what they did is they split that and made it a two-dimensional table rather than a one-dimensional table. So what they ended up with is something like this. So they split those up. And the important thing about a periodic table, we're going to be using this the rest of the semester. Every time we have a lesson, this is going to be up here. So everything vertically has similar characteristics chemically. And we're going to find out later, the arrangement of the electrons are very, very similar, which makes up the chemical characteristics of that particular element. So that's how Mendeleev and the geologist organized. They did it exactly the same way. The geologist published first, but he published in some obscure way that no one even knows he was still around anymore. And the smart one, Mendeleev, and I keep apologize for not pronouncing it right, published in the right journals, into the right crowd. So the world knew about his organizational scheme for the elements. And that's why everyone credits him with it rather than the geologist, even though he was number 2. But they both had the same idea. They're very organized people. And they just said, there's got to be more to this than just a random set of elements here, which is so very true. Okay, so what we're going to do is we're going to start taking this guy apart. So the vertical columns are called groups. And those groups come on now, why aren't you writing? Here, let's do this differently here. Okay, so all the groups have similar chemical characteristics. Now, you're going to be responsible for 4 of those groups, but every one has a name, and most of them are very obscure and rarely used. But the 4 you're going to name are used a lot. They're very commonly used. So there's no point in you learning all the obscure ones that you rarely ever see. So the first one is called I'm running out of room here. Let's see. First one is called alkali metals. The one next to it is the alkali earth metals. This one over here is called halogens. And the last one on the far right is called the noble gases. So we have alkali metals, alkali earth metals, halogens, and noble gases. Okay, so you need to know those. Those are called groups. Everything in the group has similar chemistry. So we have, now there's a lot of interesting things you can say about that. First of all, I have a tendency to have high blood pressure. Okay. And last time to the doctor, he said, your blood pressure is a little high. He said, I want you to cut back on salt. What's the formula for salt? Table salt. Sodium chloride. All right. So it's sodium chloride. Now, whenever we write a symbol that has 2 letters in it, the first one's uppercase, no exceptions. The second one is lowercase, no exceptions. Okay. Uppercase, lowercase. Okay. Now, with sodium chloride, I cook a lot. I'm really into cooking and stuff. And this is an important flavor enhancer. So the chloride makes things salty. And this just kind of comes along for the ride. This is what gives you a high blood pressure, however. So the Cl is the salty part. The Na is the high pressure, hypertension component. So I want to lower my blood pressure. With all the information you know about the periodic table now, can anyone suggest a good alternative for me when I go to Raley's to shop for a salty condiment? Knowing what you know about the periodic table. What about chloride? That's the salty part. The only way it's by itself is chlorine gas, which is not salty. Yeah. Why potassium chloride? But why is it a common salt alternative? You look, potassium, notice potassium and sodium. Now these weird names, like potassium, how do you get K from potassium? These have Greek and Latin roots. That's why there's goofy names. Okay. Potassium is in the same group as sodium. That means it has the same properties, chemical properties. So I'll go to the store now. And if I can find something called potassium chloride, I can substitute that for sodium chloride. And because the chloride is still there, it's going to make it salty. And the potassium, so this is, I'm going to talk about this in a little while. This is an ion. So to balance that negative ion, we have something that's a positive ion. So that potassium is functioning as the positive ion to balance out the negative chloride. And that's called, remember what it's called? It's called light salt. And it's right in next to the regular salt. And it's not as salty either, interestingly. Now I have really lousy hearing, smell, and taste. I don't know if I had COVID or not, but I've never had COVID, quote unquote, based on tests. And about 3 years ago or so, I had a bad case of pneumonia, right when COVID was starting to, blast away. So they went, oh my God, you have COVID, probably. So in those days, they had something called a PCR test, which is a test they have to stick all the stuff up your nose, all the way to your throat. And it's extremely uncomfortable. And then they did one nostril, and I was going, oh, God, I'm done. They go, no, we got to do the other one now. And it took like a week to get results, and I had negative. I didn't have, and PCR stands for polymerase chain reaction. And there's a little trick they use with that to make the COVID part stand out. That's the chain reaction part. Yeah, so I think I had COVID. I think that was a false negative test, to be really honest. And so because that's about when I lost my taste and smell, and besides being old. So when I flavor stuff, it's very flavorful, because otherwise it tastes bland to me. I know when I have people over, they go, oh, this is really flavorful. So anyway, this is strontium. Notice it's in the same family as calcium. Now, when there's a nuclear accident, frequently, like atomic bomb goes off, we have a Chernobyl or a 3 Mile Island or a Fukushima kind of accident at a nuclear power plant, strontium frequently becomes radioactive. Now, the problem with strontium is it's thrown up in the atmosphere in the form of fallout. And then what happens with fallout, it gradually settles downwind. And it falls down into pastures. And what are frequently in pastures? Grazing. Cows. So what happens is the cows ingest strontium, in this case, radioactive strontium. And what happens is, tell me about calcium in your body. Huh? Bones. So what happens is your body sucks in that radioactive strontium because it's in the same group as calcium. So frequently, one of the side effects of radiation poisoning is leukemia. And leukemia affects the bone marrow, which produces blood cells and all that stuff. So, and strontium is the problem here because it's in the same group as calcium. Another example. What do they make body parts out of frequently? Carbon and what else? Silicone, yeah. And the reason why it's so nice is because silicone is in the same family as carbon. So chemical characteristics are going to be very similar. Sometimes they're exactly the same. Okay, does that make sense on this grouping stuff? Okay, so what's the opposite of a column? A row. So let's talk about rows now. Let's see, okay, rows are called periods or shells. Shell is a much more useful term than period. So I'm going to frequently say shells over periods. But depending on what your next chemistry teacher decides to call it, he or she may call it period or shell. Because when we get into shells, we're going to have subshells and some, we're going to break the shell up in pieces. That's why I like to call it a shell. Okay. Now there's no periodicity at all on periods or shells. What happens is okay, the molar mass, and I'll talk about what that means in a minute here. The molar mass increases as you go to the right on the periodic table. And that's this decimal number here. Notice there's 12, 14, 16, 19, 20. So that's the only thing. Chemical characteristics are not the same at all across the period. Only the column or the group. Okay, so each square of the periodic table, let's look at carbon. Carbon. Sometimes your periodic table, like the one that you're going to be using in this class, actually has the name here. It also has two numbers. Okay, so the number of, that's the number of protons or the atomic number. And those are frequently, it's called the atomic number. That's one and the same as the number of protons. Okay, and then this last, the decimal number down here, that's the average mass of all the naturally occurring isotopes. Now, we haven't talked about what is an isotope yet and all that stuff. The reason why it's a decimal number because it's an average. Okay, so we're going to do an exercise today. I'm going to talk about how to figure this stuff out now. So there's two ways to write this stuff down. So we have carbon, and it's got 6 protons. So on the top left, that number is the number of protons. Or atomic number. That's the symbol. And down here is what isotope it is. The most common isotope for carbon is carbon-12. So this is one way to write the carbon-12 isotope. And the other way is to write it like this. Carbon-12. Now, what I'm going to have you do today is you're going to be doing both of these. And notice this is an integer, not the decimal number. The decimal number is the average of all of these. That means there's carbon-13, carbon-14, carbon-11, and carbon-12. Those averaged together based on their abundance in the natural world is 12.01. So when we talk about the atomic mass, that's this here, okay? So that's the isotope number or the atomic mass. Again, atomic masses are integers. Okay. Additionally, that bottom left number is the sum of the protons and neutrons. So how many neutrons does carbon-12 have? 6, because 6 plus 6 is 12. Okay. Now, how many neutrons would carbon-14 have? Carbon-14. Carbon-14 would have 14 minus 6 would be 8. All right. So the neutrons make up the difference between these two. P plus N. So let's talk about atomic structure now a little bit. If we're looking at carbon now, we've got 6 electrons. I'm going to talk a lot about how those electrons are organized. We have 6 electrons, 6 protons, 6 neutrons. Now the protons and neutrons, amongst 32 other subatomic particles, make up the nucleus. And that's a very, very, very tiny little spot in the middle of an atom. Now, let me give you an idea of how small that is. You have a football field, and you have a marble. 99.99% of the mass of that atom is in the marble. Everything else is, okay, electrons weigh 1/10,000th the mass of a proton. So a lot of mass, a tiny bit more mass on the neutron, because neutrons are made up of protons and an electron together. So these are a little bit massier than the protons. And this is the abundance, all the mass in the atom. So basically, when I'm stepping on this floor, what am I really stepping on? Nothing. And when we talk about the atomic model, we're going to talk about, there's a guy named Rutherford that did a very, very famous experiment. It's called the gold foil experiment. I'm going to talk about it in detail. But basically, he showed that the nucleus contains all the mass. I should say 99.9% of it. All the mass, that tiny, tiny little space. Now, what charge, who knows what the charge is on a proton? Positive. And when you put a positive by a positive, what does it want to do? It repels. Opposites attract. Positive to positive repels. So we've got these very, very strong positive charge particles in that tiny little space. So the nuclear force is what's keeping that thing together. So when we create an atomic bomb, that's what we're utilizing, is that force that's keeping those two protons jammed together in that tiny, tiny little space. Now, neutrons, by their very name, have no charge. They have mass, but no charge. Protons have almost the same amount of mass as a neutron, but they have positively charged. An electron is like a little speedster, tiny little thing mass-wise, but its charge is equivalent to the proton's positive charge, only opposite. So when we have equal amounts of electrons and protons, we have a neutral atom. Okay, so P equals E, neutral. That means zero charge. Well, what happens if we don't have an equal number of P's and E's? So if we have more P's than E's, what is the net charge on that atom? Positive. And we have a fancy name for that, and it's called a cation. Okay, so an ion is when P does not equal E. And there's two kinds of ions, negative and positive. So when the number of protons is less than the number of electrons, we have a negative charge, and that's called an anion. So we have neutral, cation, anion. Sodium. Okay, looking at the periodic table, it's hard to see over there. There. How many protons does potassium have? 19, because the integer is 19. Okay, that's the atomic number. Okay, and that's the number of protons. Okay. How about chlorine? 17. Okay, now that formula I have up there, sodium chloride, it says the sodium cation has a charge of +1. So how many electrons does sodium plus have? Okay. So sodium has 11 protons. How many electrons does sodium plus have? What's the charge on sodium? +1. That means it has one more proton than electrons. That's why it has a charge of +1. It has more protons than electrons. By how many? 1. So if sodium has 11, electrons must be what? 10. 11 minus 10 is 1. 11's positive, 10's negative. So we end up with a +1 charge. Chlorine, using the same logic. How many protons does chlorine have? Chlorine has how many protons? 17. How many electrons? 18 electrons. It has one extra electron. And we can write this as +1 or -1. Now, notice we have this together balances. If a +1 and a -1. So sodium chloride compound is neutral because the positive equal the negatives. But if we just are looking at the sodium by itself, then there are more protons and electrons. The chlorine by itself, there are more electrons and protons, because you can tell that by the charge number. So to practice that, we are going to have a worksheet. So let's do one of these together. So basically, I gave you the fundamentals, and you get to fill in the blanks. So I'm going to do the first one. You're going to learn the name of the elements, and you pull out your lab packet. Yeah, your lab packet periodic table has got the name of the element there. So what is the name of B? Boron. And what isotope? Oh, let me define isotope for you here. So isotopes have the same number of protons, different number of neutrons. So carbon 12 and carbon 13 have how many protons? 6. Because the number of protons determines the element. But they don't have the same number of neutrons. One it's got 6, the other's got 7. Okay, so those are isotopes of one another. So isotopes, very importantly now, have the same number of protons, and that determines the element's name. When you change the number of protons, the element becomes something else. So in nuclear chemistry, we do something called transmutation of elements. What happens is we change the number of protons. Hence, we mutate the element to something else because the proton number changed. And it happens all the time naturally in our atmosphere. And in nuclear power plants or an atomic bomb, we transmutate elements. Now, the alchemists, before the official scientists or philosophers, tried to take cheap metals like lead and turn them into gold. And they never succeeded. We can do that very easily now. The problem is it's very, very expensive. So it's not worth it converting it over. But we can transmutate elements, do it all the time. Has anyone had a PET scan? Any of their ailments? Who's heard of a PET scan? Okay, it stands for positron emission tomography. And what happens is they take a positron emitter and they send this chemical that comes from a nuclear power plant into your body that goes to a certain organ. And it emits positrons. Now, a positron, when it hits an electron, it explodes. And then around the PET scanning machine, they've got these detectors that figure out where those little explosions happen. Hence, they can map in 3 dimensions what's going on with that particular organ or whatever. And positrons and electrons are called antimatter. When antimatter comes together, it sounds like Star Trek, doesn't it? When antimatter comes together, it creates a ton of energy. And the energy is related to E is equal to mc squared. When the mass changes, it's converted to energy. And because it's multiplied by c squared, c is the speed of light, 300 million meters a second squared. That's a big freaking number. And you multiply that times this, the amount of energy given off is tremendous. So that a little electron hits the positron, kaboom, it's detected in this big giant machine's detector and maps on a computer screen what that looks like. Now, my friend is recovering from prostate cancer, and he just took a PET scan. And that's how they mapped out what his diagnosis is going to be and his prognosis. And he had very aggressive prostate cancer, but they think he fixed it. We'll see. Okay, so anyway, so isotopes of one another differ by neutrons only. Now, the chemistry of an element is determined by its electrons, not its protons, not its neutrons, unless we're talking about nuclear chemistry. But regular old chemistry is determined by electrons, not protons or neutrons. So the isotopes chemistry is very similar. And that's why it's similar, is because the electrons don't change. It's only the neutrons, and neutrons don't affect the chemistry unless it's nuclear chemistry, I was saying before. Okay, so that's what an isotope is. They also call that atomic mass. So when we do this little worksheet, so this is going to be the isotope. Okay, so what's the atomic number for boron? 11. Yeah. Should be 5, right? 11 is neutrons plus protons. Oh, right. Did I mess up again? That's right. But the atomic mass is the isotope number, P plus N. The atomic number is the way I wrote it? Oh. Oh, yeah. Oh, yeah. Okay, so yeah, so the atomic number is going to be 5. Okay, atomic number and the number of protons are always the same. No exceptions. Okay, and I gave you the number of neutrons. So if this is a neutral atom, how many electrons does boron 11 have? Neutral means what? Zero charge. A 5, yeah. So protons and electrons in a neutral only atom are equal because the charge is 0. So those two columns are always going to be equal. Yeah. Now the neutrons can vary all over the place. The electrons is what gives the thing its chemistry. Protons give it its mass and its element name. But the neutrons, I can repeat that now again, neutrons can be anything. Now there's a mathematical relationship between stability and the number of neutrons and protons. But theoretically, they can be anything. Yeah. You need to look at the, so boron has got 10.81 average. So that means the most common boron is boron 11 because it's closest to 10.8. So boron 10 is far from 10.8, so there's less of them. So it depends on which way the average is skewed towards. Yeah, exactly. So the mass of the isotopes differ because of neutron differences. Yeah.
So looking at this chart, find averages around.
Yeah, because it's closest to 11. What integer is it closest to? 11. Yeah, and it's farthest from 10 or 9 or 6 or something like that. So what about carbon? What's the most common isotope for carbon? Carbon 12, because it's 1201. So it's really close to 12. That means there aren't a lot of carbon 13s or 14s running around. Otherwise, the average would be higher or lower. So the most stable, i.e. common, isotopes are the one closest to the average. But this number over here is always an integer. No exceptions. Because you can't have partial neutrons. Can't have 5.5 neutrons. So it's 6 or 5 or 7 or something. So what's the atomic mass? $11, right? Which is the top number here. And that means this is going to be boron 11. Okay, so let's do another one. Let's do this guy here. Yeah. Okay, on the top is the atomic mass. That's the combination of P plus N. The bottom is the number of protons. So. See like this here? Top number is number of protons or the atomic number as opposed to the number of neutrons plus protons at the bottom or the atomic mass. Mass goes on top, number goes on the bottom. Well, on the periodic table, it's usually this is on top on the periodic table, but when you're writing the symbol out, it's flipped, which is sort of confusing. If we were writing this out in this worksheet, it would be like that. Okay. This is the way you'll see on the periodic table. Is this is on top, the bigger numbers on the bottom is usually a decimal number. On 99.99% of the periodic tables, that's the way it is. Top number is the number of protons smaller than the bottom number. However, when you see it written like in this table here, it's correct. I know. It's not wrong. It's just the way it appears in the periodic table. Huh? What?
Is there a reason?
Whoever published these periodic tables did it that way.
Gotcha.
But
Okay.
from like 150 years ago, they were doing it that way.
Gotcha.
So it's more of a legacy thing. And every periodic, you look at the periodic table in your lab packet. The small number on top is the number of protons, but when you write it out like this, the top number is the atomic mass, which is P plus N. So you see it like this. So on your next test, test 2, you're going to have a subset, something like this. And I want you to write it like this. Okay. The only time you'll see it differently is when you're looking at a periodic table. The only time. And I know that is stupidly confusing. I mean,
Use it. Fine.
you never, you're really not going to use it like the periodic table way. You're just going to be looking at a periodic table. You're never going to write it from the periodic table. And on the periodic table, there's never, the atomic mass is always a decimal number. Because it's the average. Okay. All right, so let's go ahead and do this one down here. All right, we've got a lot of blanks here. Okay. Now, again, this is a neutral atom. So what can we say about the number of protons? 39. What about the atomic number? 39. Remember, those are always the same, no exceptions. And what element is that? What is it? Oh, yeah. Okay, and atomic mass is 89. Atomic number is 39. Did I spell yttrium right? Are there two T's there? Hmm? This chemical is not used in the lab at all. So the only reason there's two Y's in there. Oh, I see what you mean. Like that, right? Okay. All right. What about the number of neutrons? Remember now, the atomic mass is P plus N. So 89 minus 39 is what? 50. Okay, so why don't you, this is all we're doing today. So I want you to get familiar with, and there's another one of these worksheets as well, dealing with ions. And we're going to hit that next time we meet, lecture-wise. Because it's a little trickier, because the electrons and the protons are not the same with an ion, by definition. Neutral means they're the same. Ion means they're different. So then how do you tell how many electrons in? This ends up being charged, and that charge reflects the difference between the electrons and protons. Okay, so go ahead and work on these. And if you download the worksheet, oops, you can see the answers. Now, this is a really good worksheet to get you familiar with looking at the relationship between protons, neutrons, electrons, looking at, oh, so this would be yttrium 89, by the way, also. Claro. Mejor que antes. Está listo para examen
No,
un poquito más práctica. Sí. Does make sense? Is this easier than dimensional analysis? Everyone thinks that. Huh? Where is it? It's under, if you go to Canvas files. Oh, you thought it was in there? Oh, okay. Yeah, this is not in your lab packet. This is an extra worksheet. You look, if you go to Canvas files, you'll see it. Well, And there are two of them there.
Yeah, there's the ion one and the red.
Yeah, so unit 2 files. And you'll see it. It's,
Just scroll down a bit.
yeah, and there's a lot of files there, so it's towards the bottom. And if you'd like to try, well, I'm not going to see you again for 2 weeks, but if you'd like to try the ion one at home, the answers are there. So. I'm going to post it Monday, not Monday morning, but probably be more, well, Monday or Tuesday, but it'll be due Thursday at midnight.
I'm in that. Or maybe it's me.
Just one. And basically it'll be sig figs, scientific notation, and dimensional analysis. So basically it'll be dry labs 1 and 2. Dry labs 1 and 2, not units, dry labs 1 and 2.
Is the third one gallium? Or 31?
Yeah.
And if the neutron is the top minus the bottom, is 39, but there's 37.
Okay, you got to figure out. Let's see which one. This is. I'm trying to figure out where gallium. Let's see, gallium. Okay, gallium has got 31. So these two are 31. And then is the neutrons filled in? Yeah, neutrons are filled in. So you're going to add these two together to get atomic mass. That's going to be 68.
Okay.
You see how I got 68?
Mhm.
Okay. And then the top number here is going to be 68, not 70.
Okay. I just thought for all those ones you were like rounding it, so.
No,
not
these are
rounding.
specific isotopes. They're not the average. We were talking about the closest one has to do with what's the most common isotope or the most stable one. That's when we were doing the rounding. Does that make sense?
So the
So it's going to be these two, it's going to be 68 on the top.
so the protons plus neutrons are the atomic.
Mass. So that's 68 there. And then because it's neutral, protons and electrons are the same. So that's going to be 31. And this is going to be gallium 68 over here, the dash 68. Okay.
So you said the atomic mass is the sum of the
P plus N. It's going to be these two together.
proton.
We might write it right up here, P plus N.
Okay,
Better.
a little bit.
He's flowing okay.
Think so.
Yeah, that looks. The ion ones are definitely different. This makes sense.
I got stuck on the rounded part.
You're not rounding on this table here. The rounding has to do with the most, when you look at the decimal number, that's the most common isotope of all of them. So like carbon is 12.01. Okay? That means that's an average of carbon 9s, carbon 10s, carbon 11, carbon 12s, carbon 13s. And because the average is closest to 12, that means that's the most common isotope. But there are other isotopes that exist. And that's what this table is. This is a unique isotope. So when you add the P plus N, that's what that isotope number is there.
It's not the same as
It's going to be close, but not the same. Because it depends on the number of neutrons. They have different neutron numbers, and the isotope number changes. The name doesn't change because the protons don't change. The only thing that changes is the atomic mass. In other words, how many of it weigh, because it has extra or less neutrons. I tried to look up this morning before I came to class the greeting. I was trying to get a site that says it. Like I do Duolingo, it's for Spanish, and it pronounces it really nice and slowly if you can slow it down.
Translate English to Russian.
Oh, okay. I don't learn a little bit of Russian. Go with my Croatian. Well, if I already have the test done, I would just send it to you, but I don't have it done yet. Where are you going?
Okay.
Well, you can always stop at like a Starbucks.
Yeah,
The place has internet.
okay. I could try to do that.
And do you have a tablet where you can write on the tablet?
Yes,
Okay. Take the test on that,
okay.
because otherwise you have to print it off.
Oh, I see. Okay.
So just do it on your tablet.
Is there a way I can just like do it on my notebook and then take a picture of it with the test, with the questions numbered?
That should work. Depends on your notebook. Just try it.
Okay, I'll try that.
Um, depends on how your notebook is set up. Do you have a black background with white lettering?
My tablet? I have the app, it's called Good Notes. But I'm not sure, I don't use it as often as I use a regular notebook.
Yeah. We'll just fuss with it.
Okay.
And you have a lab today?
No,
Oh, okay. Well, if you want to stop by lab afterwards, we can, do you have it on you have your tablet with you?
no, it's at home.
Oh.
I know.
Just try some different setups on your tablet and take pictures of it. If it looks good on your phone, it's fine.
Okay, as long as you can read it.
Yeah.
Okay, got
Yeah.
it.
And then also check for glare.
Okay,
Sometimes the screens, the different lighting will be a big glare from half of it. So anytime you do that with taking a picture of your tablet, always verify you can read it. Also, if you scan pencil doesn't scan very well. So,
do pen. But I guess I make a mistake.
well, it depends on how your tablet is set up.
Oh, okay.
Usually the contrast is pretty good on tablets.
I
So it's
see.
either white on black. The writing's in white with black background, or it's a white background with black writing.
Got it.
And I don't know which would show up better.
Okay,
And I bet you anything you can switch it to.
okay. I'll play with it.
That should work fine.
Okay, thank you.
This going okay? Okay, so this here, this is P plus N. P plus N. That's going to be 19 then.
Oh,
Okay, so it's going to be 19 up here. And it's going to be sodium 19.
so I don't have to click the three.
Huh?
I don't have to click.
3 is wrong. Where'd you get the 3 from? Oh, that's period 3. So yeah, just ignore those for now. For this exercise, those don't exist.
Okay.
Okay, is that better? Yeah, yeah. ¿Entiendes español? Oh, está bien. Necesito un poquito más lecciones, but
Está bien.
Okay, you have lab today? So you're done then.
What was this? Where on here?
Okay, so it's way at the bottom.
Oh, protons,
Yeah.
neutrons?
So that's the ion one you just clicked on now. And then click on the bottom, see it says neutral.
Right? Oh, perfect. I want to make sure I had two of the same.
There are two of the same.
Okay.
Not by design, I just, the why, you're reading, yeah. And I made this up, I was just coming up with numbers and stuff. So I accidentally did two of them the same. Okay, so that's all we're doing today. So get put a number of these under your belt, and then if you feel comfortable with it, we're done. And then lab 2, we're meeting in 104.
I think I did it wrong again. So. That is 100.
Okay. Which one is this? Trying to see, is it? It's this one here, then, right? Okay. All right. So it's 2929 and 29. Oh, excuse me. This one?
Yes.
Okay. So protons and atomic number are always the same. 4343. And then 100 is P plus N. So it's 100 minus 43. That's how many neutrons there are. Hmm? Which one?
That's first, and then the neutron?
Depends which is empty. See, because are you doing the 39 one, right? The one below it's a 29. Huh?
The neutrons are from subtracting the bottom by the top, right?
Correct.
So, and this one already has, like, it's not, it doesn't.
No. Those two numbers, I'm talking about those two numbers. These two numbers as a decimal number. Decimal numbers don't count in terms of this exercise here.
No, this one is not a decimal.
No, but it's taking the place of a decimal though. And there's a technical reason why it's not a decimal. Is it only one isotope exists? That's why it's an integer. Normally, there's multiple isotopes, and that's why the average is. Because if everything's the same, when you average it, there's no decimal. Okay, so all right, so let's ignore that for a second here. So 43. Okay, so it's going to be 43 and 43, right? Okay, and then the number of neutrons is 100 minus 43, because P plus N has to be 100. And then electrons and protons, because it's neutral, are going to be the same. So that's 43. And then what element corresponds to 43? Yeah. Okay. So that means, and what's the symbol? TT? TC. Okay. So it's going to be TC here, 100 over 43. And then this is going to be technetium dash 100. Thank you. I intend to learn that too. I want to have a nice greeting.
The pre-lab. This example that I found, what all exactly do we need to write into the?
Okay, because this one is we're doing safe stuff. We don't have to worry about first aid.
Okay.
Normally you have to do first aid, but there's salt and sand in there. For this lab, because it's, yeah. Hmm?
Basically like,
Yes, that's right. Kicking sand on the beach. Now, these are pre-lab questions. So what you're gonna do is, you grab your glasses. So let's start here. Okay, so title, purpose, and normally they don't give you the purpose. That's because of the beginning.
Oh.
Normally you have to read this to figure out what the purpose is, but in this one, they gave you the purpose. Don't worry about background. Normally they give only the background, and after reading the background, that's where the purpose comes from. And then the procedure, just, you can either summarize these or write them the way they are. And then these are more procedures. And then sometimes they're pre-lab questions and sometimes there aren't. If they're pre-lab questions, you need to do those as part of the pre-lab. Yeah, and you can't do this until you do the lab. Yeah, so the pre-lab stops there. So this is what I'm looking for. These guys,
First.
yeah, exactly. Does that make better?
So we're writing the purpose, the procedures, and the pre-lab.
Yes, pre-lab
And
questions.
we spoke, yeah.
Just the
yeah,
answers
so
to it.
we-
Okay. You want us, I saw in the example, some of like the data things were cut out and
That's
pasted
bec-
in.
Yes,
You want us to do that?
you can do that or you can just draw your own,
Okay.
either way.
Okay.
And the data you can't do till you actually do the lab.
Yeah,
And then there's gonna be calculations based on your data.
okay,
And then you'll have post-lab questions and then a conclusion.
okay. So we could write this though, and then just leave the spots blank so we have it ready.
Oh,
for
yeah,
pre-lab.
but I would class that as busy work. Turn this into a data table. You don't have to write all this
Oh,
Okay.
word stuff. Just make a, little series of boxes
Box.
and just label it,
Okay. Cool. I ordered the same notebook as she did, so.
Oh, yeah.
Nice.
Well, this is nice when you're doing graphs. And when I do a lot of graphs, but when you get to 1A or 2A, whatever class you're taking, you'll be doing more graphs.
I like how this has like the page numbers and like all of it.
Yeah.
You pay more for those though. You buy a comp book, you're looking at $1.20 or something. Oh, I'm sorry, what?
This one, it has a mass. The one I got closest was these two.
Okay, you ignore the bottom numbers on the periodic table.
Okay.
You're only looking at the top numbers now.
So it'd be actinium.
Okay, so 89 is, yes,
So I was trying to be like, okay. I see two different numbers. Which ones did I do?
Right. yeah. And the 225 comes from protons and neutrons. So these two should add up to be 225.
Okay.
Yep, exactly. And then these two are always the same. Always. Doesn't matter if it's ion or neutral.
So atomic number is always the same number as protons,
Exactly.
but protons are not, sometimes they're not the same number as neutrons.
Frequently, they're not.
Okay.
Occasionally they are, like with carbon 12
Mhm.
isotope, they're the same, but normally they're not.
Okay.
That was a bad example. I should use another one. Everyone's go, oh, they're the same. Yeah. So, is this starting to make sense?
Yeah, I just haven't seen this in years, so I'm trying to get it back in my head, because I'm like, I remember protons. I had to make like a proton and to make a model based on scandium. I picked scandium 8 to 10 years ago, and I had to do like a pipe. I used like pipe wires and cotton
Oh, yeah,
wire.
yeah. Classic. Okay, all right. How are we doing? All right, I'm gonna close this down. So this is available on Canvas. If you go to Files, Unit 2, down towards the bottom, and you'll see there's two of them. One says neutral, the other says ions. Don't download the ion one. I'm going to do that when we get back. Because it's tricky because the protons and electrons are all different, the ions. Yeah, do the neutral ones. And it has the answers as well. Okay,